Thank you very much for the invitation. Can you hear me? Right. Yeah. So it's a great pleasure to be at the Fields Institute again and in Toronto. And being Greek, I like talking about ancient solutions, although usually people, non-mathematicians of course, they think that ancient solutions means some solutions that they existed since ancient times, so they were found by ancient Greeks. So this one's not, at least to our knowledge. So anyway, so what I will be talking today is about some work regarding ancient or eternal solutions to parabolic differential equations, in particular to geometric flows. And I was told that I should keep today's lecture simple. Not that the other ones are not going to be simple. They're all going to be hopefully pretty simple. But today I will not give any proofs. I will just talk about some recent results regarding ancient solutions and some of the open problems. So what is an ancient solution, at least for what I will be talking today? An ancient solution is a solution to a time-dependent equation, in particular to what we will be talking today, to a parabolic equation that exists for all time from minus infinity to capital T. So the minus infinity here is important, and because on a parabolic equation time is not reversible, the fact that the solution has existed forever makes these solutions very special. And if capital T goes all the way to plus infinity, we usually call these solutions eternal. Now, why are we interested in studying these solutions? Because usually such solutions are obtained as blow-up limits near singularity. What is a singularity? Is usually something blows up. In geometric terms, a lot of times is a curvature that blows up. In PD terms, could be the infinity norm or some sort of norm of the solution that we are studying. And usually when we focus near a singularity, this means we shrink like to the time, so we focus in terms of time very close to the singularity. So in other words, we dilate the time, and we make at the limit the solution to exist all the way from minus infinity, because the more we focus, the more we have to lengthen the time. So at the end, we obtain at the limit a solution that have existed forever. And often classifying such solutions plays an important role into understanding the singularities. So what I would like to discuss today is ancient solutions to geometric flows, such as the mean curvature flow, the Ricci flow, and the Yamabe flow. And I will discuss both aspects, the question of uniqueness of such solutions, and also method of constructing some new ancient solutions from gluing solitons, which is self-similar solutions. And hopefully some new techniques will come up, and definitely open problems. I gave already the definition of the ancient solutions and eternal solutions, so this is already on this board. Now, of course, self-similar solutions or solitons in physics or geometric terminology are examples of ancient solutions, and definitely examples of singularities. So the most typical example, which is not very interesting, of course, in geometric sense, is the round sphere shrinking to a point or expanding depending on the flow. Other very simple examples are cylindrical, the cylinders, and this could be part of a singularity, or they are this complete and not compact type of solutions that they have cylindrical ends, not necessarily cylindrical. It could be cylindrical in the geometric sense, so they could open like paraboloids or something like that. And this could be translating soliton or steady soliton, so they translate and they don't change shape, or they could be shrinking or expanding. So, however, there are other, and a lot of times we would like to say that the singularity is modeled on such as self-similar solutions. But a lot of times these ancient solutions are not like self-similar solutions, but there are other kind of solutions that, okay, this is a very simplified picture, but they look a lot like that at different scales. So they look something like two solitons glued together by a cylinder, for example. It could be three solitons. This is a rotationally symmetric example, but you can may have examples that are non-rotationally symmetric. And so, so the question is, how can you classify such solutions, and or whether you can construct such examples if they exist. So now, a lot of times we would like to, as I said, to prove uniqueness result or classify such ancient or eternal solutions. Now, you need to impose some geometric conditions, because sometimes you have more than you want them to be. And sometimes these geometric conditions are imposed to us by the types of singularities we expect. And the simplest geometric condition is the so-called type 1 or type 2. Type 1 means that you have a global curvature bound as t approaches minus infinity, because that's where the solution starts, which is the usual kind, what you expect, for example, the spheres to have, or, the usual kind. And type 2 means that these solutions, but this global curvature, usually it's a bound on the curvature. And I don't know if I said it. And the type 2 is usually the type of ancient solutions where the curvature has the solution has curvature larger than what you expect from type 1. And other geometric conditions that come into the game are the so-called curvature non-collapsing condition, which we will see what it means, at least in the mean curvature flow. All right, so now let us start with something quite very simple, or maybe not simple, but old. And all result of Yao, dated back to 1975, says that any positive harmonic function on a complete non-compact Riemannian manifold with no negative Ricci curvature must be a constant. And so this is the analog of Liouville's theorem for harmonic functions on Rn. And you may ask the same question for solutions of the heat equation on a complete non-compact manifold, in particular on Rn. Let's say in positive solutions, no negative. So are these constant? And of course, you can easily see that they're not, there's other solutions like the ones e to the x1 plus t. It's a very simple solution of the heat equation on Rn, which is definitely not constant. So then you ask the question, how many of those solutions you have and what conditions you need to impose. And it turns out that Souple Zhang showed in 2006 that for a positive ancient solution on a complete non-compact manifold with no negative Ricci curvature, somehow this is the critical case. So if you rule out the solution, in other words, if you assume that the solution has is non-negative and has growth at infinity, little o of the distance from a fixed point to infinity with respect to the metric plus square root of t, then it must be a constant. And of course, if you don't assume the non-negativity, then you may have polynomial solutions, and a harmonic polynomial, of course, is a solution. So then, you, of course, you need to put much more restrictive assumptions. And how do you prove? Do they prove such a result? They show this Lie differentiable type inequalities in the parabolic setting, and they apply such a differentiable, like Lie differentiable Harnack inequalities on larger and larger parabolic cubes, and they take the limit. And they end up that something, because of scaling, the right scaling, something is constant. So it's, once you have this local gradient estimate, it's pretty standard to do it. Now, it turns out, it seems to me that, it turns out that for linear equations, sometimes you have more solutions. A lot of times, when you have a nonlinear equation, because something that have existed for a long time, something must have blown up, you somehow have sometimes less solutions. Not necessarily, but sometimes happens. So let's consider the next example, which is the semi-linear heat equation. And I chose to talk for a few minutes about this example because in these geometric equations, a lot of times the curvature operator satisfies an equation which is in that spirit, not in this, the same equation, of course, but in that spirit. And I'm taking for simplicity non-negative solutions. I don't have to take it, and I'm taking the exponents to be subcritical between 1 and n plus 2 or n minus 2. You can do all sorts of these results for different exponents. Now, this is a very well-studied equation. Because of the nonlinearity, there is finite time blow up, etc. So when you do a type 1 rescaling at a singularity, then you end up with an eternal solution of the rescaled equation, which is the equation star. And because of a known result of Gica and Kohn, you know that the solution, this solution W that you obtain in this particular case is uniformly bounded. So when you take the limit and you end up with an eternal solution of this equation, and you ask what are the possible bounded solutions of the equation star, which are eternal. Eternal means that they are defined from for time tau between minus infinity and plus infinity. And you expect this to be a simple problem because it's a simple equation. You have the solution is bounded, but of course it's on the whole Rn, which of course it's a non-compact space. And not only you have everything in your favor, you also have a very nice Lyapunov functional, which I haven't studied, so anything you want you have. Nevertheless, to classify the solutions, it hasn't been so easy. So anyway, which are the obvious solutions are the steady states of the steady states, which are the constants, are solutions. The steady states turn out to be only constants, and which therefore the solution, of course, is 0, and the fixed constant kappa, where kappa is this. And there are also the time-dependent solutions, which are the solutions of the ODEs. These are the trivial, eternal solutions of this equation. And actually it turns out that these are the only solutions. And all, again, theorem by Gica and Kohn, which is easy to prove because you have a nice Lyapunov functional, is that as tau approaches to minus infinity and plus infinity, you converge to a steady state. So how many options you have? Not so many, 0 and kappa. And you cannot go from 0 to kappa because something needs to decrease. So you can either go from 0 to 0 or from kappa to kappa, and that's very easy. You end up with a constant, or you can go from kappa to 0. And it turns out actually that to classify the orbits that connect kappa to 0, kappa to minus infinity, and 0 to plus infinity, and show that they are just the solutions of the ODE, which means that they are time dependent and they don't depend on space. This is a result by Merle and Zag, old result, 90-something, and it requires a lot of work. And recently, Frank Merle and Pierre Raphael, together with a student of Pierre Raphael, Collot, revisited this problem in different, I think it's in connection with type 2 blow up in some actually the critical case for n bigger than or equal to 7, reproved or find they claim a more simplified technique to classify these orbits, although it's still complicated. Now, in the geometric setting, a lot of times you will see that we have ancient solutions that they converge as t approaches minus infinity to something that looks like the cylinder, at least on compact set, and as t approaches plus infinity, it goes to a sphere. And so this is a little bit similar to this situation. So that's why I thought this is a kind of a simplified example of the geometric problems. Okay, so now let's go to something more geometric. From now on, we'll be discussing things that are more geometric. And let's start. So we, together with my collaborators, we wanted to look at the Ricci flow, first at the 2D Ricci flow, and classify the ancient compact solutions of the 2D Ricci flow. But then we saw that there were some similarities between the 1D mean curvature flow, or Gauss curvature is the same in one dimension, and the 2D Ricci flow, at least in terms of the PD involved. And so we thought first to look at the curve shortening flow, which is the simple equation. So what is the curve shortening flow? Most of you know. It's a curve on the plane, embedding on the plane. For the purposes of the talk, it will be just embedding on the plane, which in this case is the boundary of the yellow region, and evolving in a choice of a normal direction, in the right choice of the normal direction, with the speed which is proportional to the curvature of the curve. And a remarkable property that the curve shortening flow has is that it tends to make things, of course, eventually things will shrink to a point, but before they shrink, they turn to become round, and before they become completely round, they become convex. So this is a beautiful property that so far only the curve shortening flow has. We haven't discovered any other flow that has such a beautiful property. And this was a series, this was shown by Gates, Grayson, and Gates and Hamilton. There were different results. So a closed embedded curve will shrink to a round point. Now, for our purposes, we looked at first at the simplest possible case, which is a convex ancient solution of the curve shortening flow, and we asked how many of those do we have. And definitely the circles are such a things, because they are ancient solutions. As t approaches minus infinity, the diameter goes to infinity, the radius goes to infinity. But there are some other examples that we're going to see in a second. So the two examples, the other examples that accept of the contracting spheres are the so-called anguinate ovals. Anguinate likes to call them paper clips. And so here, these curves that I have in this picture, they show some sort of normalized flow, but they show somehow how these curves change shape as you go forward. So backwards in time, they are ovals, and as you go forward, they become more and more round. But as t approaches minus infinity, they look more and more oval. Now, because the curve is convex, you can easily parameterize this curve, which is convex on the plane, by one variable and one independent parameter, theta, writing it as a graph on the circle, for example, some periodic function. So theta is now an independent variable. Here, this is the equation of kappa of the curvature in curve shortening flow in terms of the arc length S. But you may write it in terms of theta, write it as a graph on the circle. And here theta is an independent variable. And so you have a periodic function of period 2 pi that it's a solution of a mixture of a porous medium type and semi-linear equation, which is periodic of period 2 pi 1d. So it cannot be so difficult. And you look for explicit solutions, and they are of this form. So kappa squared is, you see lambda, it's like a parameter. It's a function of time plus a function of theta. Very simple form. And you may say, oh, kappa squared, what is so special about the square? Actually, it turns out that this kappa squared, we call it P, is the so-called pressure in the porous medium terminology. And it's easier, actually, when you work, you try to classify to work with kappa squared, which is the P. And so what we proved back in 2010 with Hamilton, Ricci Hamilton, and Natasha Seshum is under convexity, and of course all, under convexity, the only ancient solutions which are not the spheres are of this form, a function of space plus a function of time, hence they are exactly those paper clips. How did you prove, or did we prove it? It's simple, the proof is simple. It turns out that in this case you have a lot of monotone integral quantities that you play with, and you also use the fact that as t approaches plus infinity after you rescale, you see the sphere and you know exactly in which rate you see the sphere, and anyway you play around and you prove it. The proof is simple. Now, you may ask whether the convexity is necessary. Of course, without the convexity, you don't have the nice PDE with an independent variable. And so you cannot work with a PDE. And it turns out that without the convexity and without some non-collapse condition, you may have other solutions. And Sigurd Angenet has a YouTube video of a solution that looks like that. So the curve is the boundary of the yellow region, which is this red curve. And as t approaches minus infinity, it winds more and more around. And as you go forward, of course, it unwinds and eventually it becomes circular. And so when you remove the convexity, you may have other examples, and we thought it does make much sense to work on this problem. So now what happens in higher D? In higher D, it's like the mean curvature flow. And so let's, what is the mean curvature flow? Most of you know, but it's the evolution of a hypersurface in Rn by its mean curvature in the right normal direction. And let's say again that we would like to talk about ancient compact solutions to the mean curvature flow. And let's say that we would like to get some information about them. Now, mean curvature flow is well known for having many exotic singularities, and so you expect to have a lot of solutions in principle, ancient or not ancient. So you need to impose some geometric conditions if you would like to classify such ancient solutions. And these geometric conditions, of course, are related to the study of singularities. So one of these conditions that they come in the mean curvature flow, and they also come in Ricci flow, is the so-called alpha non-collapsed condition. And this was first introduced by Weimin Sheng and Sujia Wang, and independently by Ben Andrews. So what it means that, let's say you have a compact solution, which is the compact body, which is the boundary of kappa, of K. And so this alpha non-collapse condition means that at each point on your compact surface, you would like to put a ball from inside and outside of radius alpha over h. H is the mean curvature of the body, of the surface at the particular point P. And you want the alpha to be uniformly bounded from above and below as t approaches minus infinity, for an ancient solution to be alpha non-collapsed. Now, Robert Hasselhofer and Bruce Kleiner showed that if you have an ancient compact and alpha non-collapsed solution to the mean curvature flow, it's convex. So it's quite strong to have alpha non-collapse, so it imposes convexity, and it's easy to show that convex, compact, and self-similar solutions to the mean curvature flow are the spheres. So, but nevertheless, there are non-self-similar solutions that they're not the spheres, and they're, of course, alpha non-collapse and compact. And we know them already from the curve shortening flow, the paper clips. So they are kind of the higher dimension analog of the paper clips, although we don't know exactly who they are. So anyway, I'm giving the definition. I'm saying ancient oval to be any compact alpha non-collapse solution to the mean curvature flow, which is non-self-similar. We call them ovals. And the question is, which are those? Right? In 1D, they are in explicit form, and then they're so-called paper clips. In this, here, we don't actually know. So the problem is to find all of them. And now we have some examples. So Brian White in 2003 came with a proof of the existence of ancient compact, let's say convex solutions to mean curvature flow, which are not the spheres. And we will be calling them the White ancient ovals. Now his proof was not so clear, and was not so detailed, I will say. So Robert Hasselhofer and Hershkovitz in 2003 gave a very nice clean proof of this result, and they also established some of the properties of the White ovals. So so they proved the existence of ancient ovals, and which have a OK cross OL symmetry, and we will be calling them the White ancient ovals.
Are they convex?
They are convex. These are convex. And so, Angenet in 2012 showed formal match asymptotics of these ovals. And they proved that they looked, his asymptotics showed that there are three regions. There is a cylindrical region, we'll be calling them the parabolic region. Then there is an intermediate region, which is the longest, is where the solution looks like an ellipsoid, and very close to the tip, at a very tiny scale, you see a soliton, the so-called Brian soliton. The ball soliton. Brian soliton is for the Ricci flow. Okay, so now, jointly with Sigurd Angenent and Natasha Sessom in 2015, we actually showed that all alpha non-collapsed solutions, compact ancient solutions of the mean curvature flow with O1 cross O1 symmetry satisfy this formal asymptotics. And our goal was to establish the uniqueness of such, to show that under these conditions, the only ones are the white ovals. And now part of our most detailed asymptotics, so our detailed asymptotics imply detailed bounds, actually estimates on the diameter of the solutions as t approaches minus infinity. It shows that the diameter has this growth, and of the maximum curvature. And so in lecture, the third lecture, I will talk more about this result. And I will also talk more about the question of uniqueness of ancient ovals. So there are two questions here. Of course, they are related. If you want to show the uniqueness, you need to show the rotational symmetry, and you need to classify all rotational symmetric ones. So recently, with Sigurd Angenent and Natasha Sessom, we showed that any ancient oval with O1 cross O1 symmetry, and ancient oval is alpha non-collapsed and ancient compact, is unique up to scaling and translations in time. Therefore, are these white ovals constructed by Brian White and Hasselhofer and Herskovits. And in the third lecture, I will give an idea on how we prove this. Still, the question is the rotational symmetry, which is not known. It's an open problem. People are working on that. And it was just posted on the archive, a new result by Theodora Burni, Max Langford, and Tinalia, where they show the existence of ancient collapse solutions that as t approaches minus infinity, they look like pancakes in the appropriate scaling, where the diameter of pancake becomes larger and larger. And they also prove the uniqueness of such solutions, right? So they constructed compact convex ancient solutions with O1 cross O1 symmetry that lie between two planes of distance pi, and they establish the uniqueness of the solution. So I haven't read the proof yet because I just saw the result, but it's an interesting result. What? They prove the unique. What? Yes, they establish the uniqueness in that with these properties. I mean, the ones like, of course, the fact that yes, uniqueness with the property that they lie between these two planes somehow. Excuse me? They don't use uniqueness? Okay, interesting. I told you I haven't read the paper, but they send me the paper because I discussed with them a few months ago, and they were doing and they sent me the paper and they said that they do uniqueness. Okay, right. So I think they claim it at the abstract, right? But you're saying that they. Okay. All right. So you should look at the paper for more details. Okay. So I will look at it maybe tomorrow. Maybe by Thursday I will take a better look, and I will see. Anyway, so now we said today no more details, so let's go to another flow. Ricci flow. So this was our original problem. So we wanted to look at the Ricci flow and study the ancient compact solutions in 2 and 3D. Now in 3D it's still an open problem, and in 2D we did it a while ago. So let me at least tell you what we did in 2D. So, but okay, for the most of you must be familiar with the Ricci flow, but let me briefly tell you what it is. The Ricci flow is the evolution of a Riemannian metric, Gij, on a manifold, on a compact, in the purposes of the talk it will be compact, by its Ricci curvature with the right sign. And this was established by Richard Hamilton in 1981. He had in mind to give a proof of the Poincare conjecture, the geometrization conjecture, and we all know of the very important works of Richard Hamilton and later of Perelman for proving the geometrization conjecture. Many important works by many people, but I can't discuss them right now. So for the purposes of the talk right now, we will discuss ancient solutions of the 2D Ricci flow. So in 2D, the Ricci flow is special because it comes from the fact that the Ricci curvature is 1/2 the scalar curvature multiplied by the metric. So this is a very special case. And it's a known result by Hamilton and then Chow that after renormalization of the metric, the compact manifold evolving by the 2D Ricci flow becomes spherical. So hence, because everything is so special in 2D, you can parameterize the metric by U, which is a conformal factor, multiplied by the standard metric on S2. And so this is the standard metric on the sphere. And therefore, you end up with a very nice equation it's a logarithmic fast diffusion equation on S2, which is U sub t is Laplacian of log of U minus 2. The 2 comes from being on the sphere. And studying the ancient compact solutions of the 2D Ricci flow, it's equivalent into studying the ancient solutions of this very nice PD, where this is the Laplacian on the sphere. So these are solutions of the S2 from -infinity up to some time t. And of course, the contracting spheres are always there. They are examples of solutions. In these settings, they are just the solutions that they are just a constant, a function of time, multiplied, U is just a function of time. And so these are the type 1 solutions, of course, always. And then there are solutions, type 2 solutions. We call it the King-Rosenau solution, which as metrics on the sphere, their rotation is symmetric, so they just depend on one variable. And you see are a function of time plus another function of time multiplied the function of psi. Psi is one of the variables on the sphere, inverse. And why inverse again? Because the U inverse is what comes as the so-called pressure for this equation. Again, this equation has also a physical interpretation, and so studying this inverse of this, which we call pressure, although it has nothing to do actually really with pressure, it makes sense for this equation. All right. Now, this King-Rosenau solution, both King and Rosenau are applied mathematicians, and they found the solutions much before there was a connection between this equation, this logarithmic equation, and geometry. They studied the equation of this logarithmic fast diffusion equation on R2, and if you write this on R2, you end up that the pressure function is a function, it's a polynomial in the radial variable with coefficients that depend on time. So anyway, so they have a special form, they're solutions of a special form, and they found them. It's explicit, and geometrically, again, it looks like this. So it's one cigar soliton, so half of it is a cigar soliton, another half is another cigar, and they're kind of joined with a cylinder. And as t approaches minus infinity, you see exactly this, and you don't need to rescale in this case. Right? And so as t approaches minus infinity, this moves outwards and that moves out, it becomes longer. Again. So, and in 2012, with Hamilton and Celsu, we show that the only ancient solutions of the Ricci flow on S2 are the contracting spheres and the King-Rosenau solutions. So again, why did we think that, okay, oh, here it is, yeah. You see, okay, the reason we first did the curve shortening flow is because, again, this equation in 1D higher, right here is on S2 before it was on the circle, it's kind of a Paul-Smith type equation. But in this case, the proof is much more complicated. It involves a lot of estimates and geometric arguments and PD arguments, and I don't really have time to discuss it. So it's much more complicated than the curve shortening flow, but it also uses the fact that we know we have an explicit form of the solution. So at the end, we find a quantity which vanishes on our solution and vanishes on all the other eternal solutions or ancient solutions. And then we show that somehow any ancient solution, apart from the spheres, must satisfy this quantity equals to 0, then we recover them by that, from that. But in the meantime, it's like a complicated argument. Now, in the 3D Ricci flow, the question is still open. So the conjecture here is that the only ancient compact and kappa non-collapsed solutions. Kappa non-collapse is some sort of non-collapse condition introduced by Perelman. Okay, it's not the same, but in the same flavor I described for mean curvature flow. And are the spheres and the Perelman solution, which is the analog of the King-Rosenau solution in higher D. And this is still an open question. Again, in this case, the solution constructed by Perelman, which is the one we're after in the uniqueness result, is not given in explicit form.
Does this Perelman solution also look like going together Solitons?
Yes, it looks like the so-called Bryan soliton on one side, Bryan soliton on the other side. The Bryan solitons, the cigars, let's say, they don't open up. The previous, like in the 2D, the cigar looks like cylinders at infinity. The Bryan soliton open like a parabola. So, but yes, it's the same idea, like in the mean curvature flow. Yes. So anyway, and just I would like to close with the Yamabe flow, just because it's different, a little different than the Ricci flow. So in the 2D Ricci flow, because the as I said, the Ricci curvature is more or less the scalar curvature. It's like evolving a metric in a given conformal class by the scalar curvature in 2D, which is in some sense the Yamabe flow in 2D, right? And so what is the Yamabe flow? The Yamabe flow is the flow where you evolve a metric in a given conformal fact, in a given conformal class, by its scalar curvature. And this was introduced by Richard Hamilton as a tool to prove the Yamabe problem, which was shown actually by elliptic method by Ricci. And Simon Brendle and Rugan-Yib and Chow and Svetlana and Struve have important results regarding the convergence of the Yamabe flow to a sphere. Of course, Brendle was the one that proved the complete result with assuming a mild technical assumption dimension n bigger than equal to 6, and he showed that the converge compact in the compact case you have convergence to the spheres. Now, from the PDE point of view, you have a nice PDE, and if you restrict in the conformally flat case, or the case where you have a metric on Sn, you can write it in this nice form. So you have a fast diffusion equation where this is a critical exponent on the sphere. So this is the simple case where you have the Yamabe flow on Sn, on the sphere, and not on any manifold. And we would like to ask which are the ancient solutions of the Yamabe flow on the sphere. Of course, you can ask the same question on any manifold. And again, you have the same picture. You have the contracting sphere, and you have the same kind of solution you have for the 2D case, for the Ricci flow, which was shown again by King. Has nothing to do with Yamabe flow. It had to do with the porous medium, the fast diffusion equation. Again, the same idea. But in this case, you have many more solutions. So actually, it turns out that in the case of the Yamabe flow, you have many more non-compact solutions, so half of them. All right, so these the solutions that they give the raise to these ones, like half of it, extending all the way to infinity, and on the other side are these complete non-compact solutions that they are shrinking. They are shrinkers. They are shrinking solutions, right? But they are complete non-compact, so they look like cylinders at infinity. And it turns out that for this equation, you have an one-parameter family of non-trivial self-similar solutions. By non-trivial means you change the self-similar exponent, which is kind of unusual to have, like, for any real number to have a self-similar exponent. So anyway, you have a lot of solitons. Therefore, we were able to construct a 5-parameter family of ancient compact solutions coming from gluing different. You can glue it one solid on one side, one solid on the other side, and a cylinder in the middle. And finally, so these are type 1 ancient solutions. So classifying doesn't make sense because we have so many. And we were also able to glue spheres as t approaches minus infinity, joined with little necks, and construct type 2 ancient solutions. So we call them the towers of bubbles. So as t approaches minus infinity, after you normalize with a volume, let's say, they look like towers of spheres. So these are type 2 ancient solutions. They are complete. They are compact, and they, of course, the curvature operator changes sign. So you have so many solutions. It doesn't make sense to try to classify them.
Doesn't that work in the Ricci flow? That spheres come together?
Why it doesn't work in the Ricci flow? It doesn't. You may say, why doesn't it work in the mean curvature flow also? You know, that's the fair. Because, yes, it's just, it's a very special case that it works here. So, you know, it's like very, very simple properties are violated. So it obviously doesn't work in any of these flows. It only works in the Yamabe flow. Yes. And so there is something, okay, there is an interesting example by Brendle and Capouleas in the 4D Ricci flow, which is given by parabolic gluing, but it's very, very different than what we, I mean, the spirit is different, but still it's a parabolic gluing result. So when we did this problem, actually, we thought that it was a good example of a construction of a parabolic gluing result, a little bit in the similar spirit of the Capouleas and others, elliptic gluing results. Anyway, to conclude, we discussed ancient solutions to parabolic PDE, especially to geometric flows, and these are specific type. These are quite special solutions, and sometimes it would be nice to know how to prove uniqueness because it's related to the problem of classification of singularities. So what I think it would be interested is to find new techniques of, for example, proving the rotational symmetry of such solutions in case it's true that they are rotationally symmetric, or prove uniqueness of such in certain classes of solutions, especially in the cases where the solutions are not given in explicit form, like in some of the cases I discussed. And of course, it's always interesting to be able to show that under some conditions, such solutions are the solitons. So I would like to stop.
I have a question about the stability of these other solitons, the parallel solitons, which go together. So is it clear that if I have a singularity formation in the Ricci problem,
Yeah.
and I see the parallel ancient solution, is it clear that it wasn't the ancient solution itself to begin with? That this model is somehow generic singularity formation? Not clear. So
it's...
I'm asking, let me just ask, if I do a blow of a singularity and I see the parallel solution, then maybe the original solution was also the parallel solution.
Yes.
It's clear that that's not the case.
I mean, the Perelman solution will be like the sphere when you write. I mean, I think in a lot of times when you do a blow up in this, you're not going to see the Perelman solution actually in some cases, because these Perelman solutions may not. Like you're not going to see the Perelman solution, but in the Perelman solution, you're not going to see the Perelman solution because you're going to see the sphere.
I see. So even that.
Yeah.
So it might be the case that I will never see it.
Yes. Yes.
So that is that a fact that I will not see that, no matter how I do the blow up.
Yes, that's a good point. I think I don't know exactly, but yes, but right, yes, but. Right, but you're not going to see, but I don't think you're going to see the Perelman solution. Yeah.
I have a question. Unless I missed something, all these ancient solutions you showed us are self-similar, they're put by gluing together self-similar.
Mm-hmm.
So is it reasonable to expect that maybe one can show that any ancient solution has to be obtained by gluing together some finite number of self-similar groups?
Yeah, I have no idea, because, right, for example, the pancake solution is a little different, right? It's like by rotating. And plus, there can be, maybe that's the ones we know how to construct. right? So we know so little, so it's I wouldn't make any such a claim. It's just too general, I think.
So from purely PDE point of view, if I take the parameter as the curvature solution, that's time minus 1. I look at the linearization of the Is it stable or is it only slightly more positive?
You know, if you take the ancient solution.
Yeah, the ancient solution, the time minus 1. I'm going to take it from the PDE or the time point of view.
I don't know. What I know is for the pieces of the solution, first of all, at minus 1, who knows? I don't think anybody has studied. The only thing we know is as t approaches minus infinity, it has 3 pieces, right? Like for the mean curvature flow, the oval, and in the middle you have the cylinder, which is not stable. And then you have, at the end, you have the soliton, which is stable. But you don't know if it's...
You don't know if the whole thing is stable.
No, you don't know. Actually, if you knew it, then maybe you know the uniqueness. I mean, yes. You will know the uniqueness given the asymptotics, but you don't. Maybe it could follow from uniqueness, but, right. That's a good point, actually, yeah. It's a little bit what we show, actually, in the rotational symmetric case, because we saw, like, you may ask the question, if you start with one of the wide ovals, right, and as t approaches minus infinity, you have another solution which is very close in the right setting, in the right norm, to the ancient oval. Is it the same? Modulo the two dilations, the dilations and translation in the original time, right? And okay, this is more or less what we prove.